Today we are talking about the mole. I'm not talking about a little rodent. I'm not talking about the little brown spots on our bodies with hair. Okay. Mole is the amount of substance Anybody have a way to measure moles? Anybody ever see a way to measure moles? What about in lab? There's not. So why the heck do we learn about it? Because there's a magic number. You guys like magic, right? Okay. 1 mole, and by the way, we abbreviate mole to be MOL. Much better. But don't abbreviate molecule as mole, please. Okay? So 1 mole of anything is equal to 6.022 times 10 to the 23 particles of that thing. Okay? And we're going to learn how, this is just a conversion factor. This is how we might convert to moles. But in reality, we don't use this much. But think about this. If we have 1 mole of, let's say, water, it's like that much water in our container, okay? I know that depends on how big that container is, but let's say a 600 milliliter container, okay? About that much. If we take a container the same size and put sugar in it, then it's about that much sugar. Well, that's weird. Why is that? Because sugar molecules are bigger. So it's going to fill more, yeah? But that's still 1 mole. Here we have 6.022 times 10 to the 23 particles of water. And here we have 6.022 times 10 to the 23 particles of sugar. Okay? So because of this ratio, that helps us to be able to make predictions. And that's really what we use it for. Okay? To make predictions. So used to make predictions. And not just any prediction, but pretty good predictions. Pretty close. So for example, a week or 2 ago, had family over, we made dinner, we cooked salmon, and well, we had to, so we found out how many people was coming over, and then we go to Costco, get their salmon, and think, okay, so how many of these should we get? We don't do this a lot. So we got some salmon, it's like, do we have enough? It's embarrassing if you invite everybody over and they not have enough food, right? So we just, okay, just get a couple extra. But there's a problem. Salmon is not cheap, right? That's a lot of money. But luckily we like salmon anyway, we can use it, right? Then you have to throw it in the freezer, then it's not fresh, and then it's whatever. Okay. So if I can make a better prediction, then I wouldn't have so much left over, right? Like we did. Okay? And that's what we're learning today, is how to make sure we don't have too much left over. A lot of waste. Because you waste stuff, you just lose money, right? And anyway, so that's the purpose of what we're learning today. Good? So since this is our conversion factor that we just barely got, let's first of all learn the different names for particles. Representative particles are particles that represent a particular type of substance, okay? And really there's two main ones. We might use three, okay? So one type are atoms. Atoms represent the particles for elements. Maybe I should write that a little differently. Particles for elements, or of elements. Does that kind of make sense, guys? A single particle of an element we call an atom. Because an atom is the smallest particle of an element that retains its identity, right? Okay. And then a molecule, I'm sure you've heard that before. Molecule, please don't abbreviate that as MOL or MOLE. They're different. So a molecule is a particle that represents a compound, more specifically a covalent compound, but a lot of times they get used for any type of compound. Have you heard of a molecule of salt? It's not the correct name for it, but everybody uses molecules of salt. So are we okay with just calling all particles of compounds just molecules? Or do you want the real name? Both? Okay. I'll give you the real name, but we'll probably just use molecules. Sound good? Not to fit in with the rest of the world, but we got enough on our plate, right? Okay. So we'll call this covalent compounds. And particles for ionic compounds are called formula units. Can be abbreviated if you want. Okay. These are particles of ionic compounds. But again, ladies and gents, I'm okay if we just use molecules. Okay? When I started teaching 15 years ago, I was pretty strict on this. No, that's the right. It doesn't matter. Okay? It really doesn't. Just a name. Okay? And the last one are ions. These are particles of ions. Okay? Of a charged atom, right? All right, we good with these names? So you guys remember dimensional analysis? Just conversion, right? That's what we're doing today, conversions. And when are we going to stop doing conversions?
Never.
When we're done with this class. Or probably not. If we're going into nursing, you're probably still going to do it, right? Anybody do it in your job right now? Conversions?
They usually have systems in nursing for that.
Okay. Okay. Yeah, you do it? Yeah. So you're gonna do it. So you got to know how to convert. You might not have to know how to convert moles to grams and grams to moles and all that stuff, but okay. So let's do an example. We good? All right. So let's say we have 7.303 times 10 to the 24 gold atoms. Well, I should say, actually, atoms of gold. And I want to know how many moles of gold do we have. So remember when we did dimensional analysis with the dosing problems? First step, what is it that we're looking for? With the correct unit, right? We have to know that. If we don't know that, we'll never get there, okay? And then we also have to know something else. If we don't know anything, you can't solve the problem, right? You got to know what you know, okay? Where do we start? After those first two steps, do you remember? Start with what we know or don't know. What we know. And what do we know? That guy right there. We also know one more thing. Just from today, we know this conversion factor. Yeah? So we know 1 mole is equal to 6.022 times 10 to the 23 particles. In this case, what is it? Atoms, right? 1 mole of gold is the same as 6.022 times 10 to the 23 atoms of gold. Good? So let's start either with this or with this. Which one do you want to start with? The top one, because it's simpler, right? 7.303 times 10 to the 24 atoms of gold. And ladies and gentlemen, write down everything. I know that's quite large, right? A lot of stuff. Write down everything. Because in the end, if we don't, it'll confuse us, and we might end up with the wrong unit or the wrong value, okay? So keep everything organized. Things work way better when you're organized. All right. So do we want atoms of gold in our answer? Where does it go? If we don't want it, where do we put it? On the bottom. So atoms, we know atoms to what? To moles, right? We use that one. We're not going to use that one again. See if we can use this one. So 1 mole of gold is the same as 6.022 times 10 to the 23 atoms of gold. Kind of squished it in there. Atoms of gold go away. Are we comfortable with converting, guys? Okay. and then we just divide those, and we get 12.13 atoms of gold. Good? Can you all type those in your calculator still? Y'all remember how to do this? Yeah,
It's a gold.
sure is. How do we know? Because that's the only unit we have left, isn't it? I was just checking to see if you was with me. Sorry. Yeah, moles of gold. Takes the guesswork out if you write everything, right? You just have to look at it. We good? Okay. And this is just a single step in where we're going, like everything, right? How do we feel about that? Do one more? Yeah, let's do one more. Unless you have any questions on that one. Okay. Let's say we have 2.88 moles of silicon tetrachloride, and we want to know how many chlorine atoms do we have? Where do we start? No idea? Yeah. Yeah, start with what we know. That's the only value we have up here that we know. Start there, that's what we know. It's hard to start with what you don't know. 2.88 moles of silicon tetrachloride. We don't want moles, so where do they go? On the bottom. Moles of silicon tetrachloride. What can we convert to? Can we convert straight to chlorine atoms? Do you know how many chlorine atoms are in 1 mole of silicon tetrachloride? I don't either. Okay, so only use the conversion factors that we know. Good? So we know how to convert moles to what? What did we just learn? Moles to particles. What are the particles of silicon tetrachloride called? Silicon tetrachloride is covalent compound. These are called molecules, or any compound we can call molecule, right? It's not a single element, so we're going to convert to molecules. Don't abbreviate it. Are we good? All right, now what numbers do we use? What number goes on top? Yeah, 6.022 times 10 to the 23 molecules or particles is the same as how many moles? 1 mole. That's what a mole means, right? Are we okay with this? Okay. Moles go away. Is that what we're looking for? No, so what does that tell us we got to do? Keep going. Keep converting. Okay, we don't want molecules of SiCl4. Do we know how to go to atoms from molecules? Let's say we have one molecule. In one molecule, do we know how many chlorine atoms we have? 4. Do we see that? So we know this, but we've never used this, so it's like, well, what do we do, right? So we got to just think about what we know. 4 atoms of chlorine. That goes away. That's what we're looking for, so we can stop. So we multiply those, divide those, and nothing to divide actually. And we get 6.94, we can round it to, times 10 to the 24 atoms of chlorine. Can y'all get that in your calculator? Make sure you can. How do we feel about that? Easy, hard, somewhere in between? Yeah. Sandy.
That answer, the 6.94.
So we take 2.88 and we multiply by this number, 6.022 times 10 to 23, and then we multiply by 4. And if there was numbers on bottom, we divide by those numbers. They're ones, but that doesn't change anything, right? Did you get that? Try it. And if you need help, I can help you get there. Do we understand how to set up this problem before we multiply? Okay. Is that what everybody's getting?
No, can you do it again? So, 2.88,
2.88
multiply that by 6.022 to the 10th, times 10 to the 23rd.
So here's how I type it in, guys. If you can type it in using less buttons on your calculator, less chance for error, right? But there is more than one way to type it in your calculator. But let me show you how I do it. 2.88, then I'm going to push the multiply button because the other number's on top, right? And then 6.022, instead of writing times 10, a button on your calculator, on your scientific calculator that means times 10 is EE or EXP, or a button that says times 10 to the x power. Whatever your calculator says. And on your calculator, it's second, and then the button right above number 7. That means times 10 to the power of, and then we have to put in the power, which is 23. And then we multiply again because the next one's on top. Type in 4 and then push equals.
Okay, thank you.
There are more than one way to put it in the calculator, but that's the simplest, I think. Less buttons. Okay? But I know some of your calculators will show everything how it is, and it'll be easy to tell if it's right or wrong. That's okay. You can just type in times 10 raised to the 23rd power. It's fine. It'll still work that way. Okay?
Thank you.
Mm-hmm. We good? All right. Do you want to practice some of these on section 1 on the worksheet? Let's do it. or do we need to do another one together? How you feeling? Ready for practice?
I mean, if it's just gonna be like one or two steps, like you got us here, we could just start with that.
Well,
you know?
that's all the first one is, yeah. We're gonna get to more. So there will be one of these on the exam. Probably just one. And probably no more after this. What? Why do we do this then?
Make us think.
I'll show you. This isn't a useful calculation, but this number, 6.022 times 10 to the 23, it helps us to make better predictions. Helps us to know about moles. Like I said, we can't go to the lab and measure how many moles we have, right? So this is why we can just convert and use moles to help us, okay? Make better predictions. This one down here is a little tougher. Well, we should be able to get it if we remember what we learned last unit. But that one's a tough one. But you should be able to do the rest without any problem.
So, like, we're not just going off of the atomic weight.
No, not right now. Right now, we're just going from moles to particles, particles to moles. That's it.
Okay.
The only conversion factor we're using is the 1 mole equals 6.022 times 10 to the 23 particles. That's it so far. this says we want the number of moles that are in this many atoms, right?
Mhm.
You just put that number with moles.
Oh,
That should be atoms,
okay.
right? And then
I want to multiply that, and then I want to get rid of atoms. With this, I want to have moles.
yeah, that's it.
So this is the correct setup. I mean, just not.
Yeah,
in the
yeah,
right way.
yeah, yeah.
Okay.
Yep, that's it. Here are the answers up here to see if you're doing it right.
I got a different answer for the last one, the ions. So I must have done something wrong.
So for the bottom one down there?
Mm-hmm.
Yeah, that one's a tough one. But let's
Yeah.
see, let me see what we did here. So 0.38 moles of this. One mole for that many not ions.
No.
What are these called?
Molecules?
Molecules. So,
Okay.
right?
Because it's a compound.
Yeah, it's not an
Mhm.
ion. But this is an ionic compound, right?
Mm-hmm.
How many ions are in one of those?
Oh yeah, I don't know.
Na plus NO3 minus. There's no parenthesis here, so there's only one of those and one of those.
Mm-hmm.
So there's two of those, 2 ions for every one molecule. Do you get that?
I didn't. Okay.
So we have to do one more step.
Yeah, I thought. So I got 4 because I thought it was 3 and then that one.
Nope. This is not, oxygen's not an ion. The ion is nitrate. Because the metal is one and the non-metal is the other one. An ionic compound only has two ions,
Okay.
or a minimum of two. If you had something like this, now there's parentheses here, right? There's two of these ions and one of those ions, so that's three,
Okay.
right?
Yeah.
But if there's no parenthesis, it's just one of them. Remember that?
Okay. All right, very good, thank you.
Okay, do we have any questions? You want to try this ion one down at the bottom? Or do you want to try a different one? You tell me. Or do you want to keep working? Okay. All right, it says we have 0.38 moles of sodium nitrate. And we got to find out how many ions we have. Is the particle of that an ion? No, that's a compound, right? So we call those either formula units or molecules, either one. We'll just you guys want to stick with just molecules? Okay? So every 1 mole of sodium nitrate, we have how many molecules? 6.022 times 10 to the 23, yeah. Okay, so that goes away. All right, do we have any ions in sodium nitrate? What kind of compound is sodium nitrate? It's ionic. It's made of ions. How many ions are in 1 molecule of sodium nitrate? 2 of them. We split between the cations and the anions. There's only 1 here, right? 1 sodium. How many nitrates are there? Yeah, why is there only 1 and not 3? There's no parentheses, right? So there's only 1 nitrate. So that's 1, 2. So we can go for every 1 molecule of sodium nitrate, we have 2 ions. Are we going to call them ions of sodium? Ions of nitrate? No, they're just ions, right? Because they're different, so we can't name them one or the other. We'll just say 2 ions. Does that make sense to everybody? Questions on that? So that was kind of like the ones where we found the number of chlorine atoms, right? We had to break it up even further. Good? But as far as that goes, that's as tough as we'll get. Okay? Questions? Any? Yeah, you know.
I do have one question. I'll have you face this by apologizing to the class because I was 10 minutes late. So just for my notes, so it's always going to be, the formula is always going to be 6.022 times 10 to the 23rd power.
Equals 1 mole of
Equals 1 mole. No
whatever.
matter whether it's, sorry, just one second, just a picture. Whether it's an atom, a molecule, an ion,
That's right.
that's always going to be the formula.
Yep.
Okay.
But you see here, this is not an ion, so we have to break it up even further, right? So we got to know that. We got to know the names for the different types of substances. Good? Any other questions on this section? Okay, let's move on. Next, we're going to talk about molar mass. Molar mass is just a conversion factor. What do you think it is? Let's break this word up. Molar mass. The mass of what? A mole. That's it. This is the mass of 1 mole. Okay? So what's the molar mass of carbon? Does anybody know? Well, let me ask you this. What's the atomic mass of carbon? Can you find that on your periodic table?
What was the question again?
What is the atomic mass of carbon? 12.01. Should we use 12.01 or should we just round that to 12? It's just an average anyway, right?
Yeah.
That's basically 12. Now listen, on the test, how do we know? Should we round? Should we not? I would say if it's really darn close, like 12.01, yeah, we can round. But if it's like chlorine, which is 35.45, should we round to 35? No. If anything, round it to 35.5, right? But what happens if we're not sure if we should round? Then what? Then don't. You don't have to round, okay? Good enough? So keep it simple. So this is 12. We'll just say 12. 12 what? Did we learn about the what?
6.022.
No. Nope. Atomic mass is measured in what? So we learned that number today. That's the particles per mole. But this is mass, right? What's mass measured in? Grams, right? Can we say it's 12 grams is the atomic mass? Wouldn't make any sense. 12 grams is way more than what an atom is, right? So it's 12 grams for something. Any ideas? $12 grams per mole. That's what it is. You remember in the book it says AMUs? Do you remember that atomic mass unit? The length of this table is 5 distance units. Sounds dumb and not just my voice, right? Okay? Doesn't make any sense to say atomic mass units. The atomic mass unit is grams per mole. Are we good? And that is the molar mass of carbon. We call it the molar mass. So why don't we call it the atomic? What? Because we don't necessarily need to find the molar mass of an element. But what's the molar mass of H2O? Think we did this before, but we'll do it again. Maybe not for water. Do you remember what we do? The atomic mass of hydrogen is what?
1.008.
What should we say that is? 1? Yeah, that's even closer to, okay. And there's how many hydrogens? 2, so we're going to multiply that by 2. Plus oxygen is
16.
basically 16. We add those together and we get 18 grams per mole. So we got a bunch of conversion factors right on the periodic table. Some of them we have to figure out, but they're there, grams per mole. So if we want to convert grams into moles, we got it. Or if we want to convert from moles into grams, we got it. Do you get that? Let's practice some. Okay, let's say we have 1.58 grams of ammonium hydroxide, and we want to find out how many moles of ammonium hydroxide we have. Okay. So it's just a conversion problem. So we're going to start with what we know. 1.58 grams of ammonium hydroxide. We do not want grams in our answer, so they go where? On the bottom. And we want to convert it to what? Moles. And we know a conversion factor, grams per mole, right? It's not 18 because we're not dealing with water, right? But we can figure this out. Moles of NH4OH. So let's figure this out. Nitrogen has an atomic mass of 14. We'll just round it to 14. Hydrogen has an atomic mass of 1. Multiply that by 4. Plus oxygen has an atomic mass of 16. Plus another hydrogen, atomic mass of 1. We get this and we get what? 35 grams per mole. So the 35 goes down on bottom. 1 goes on top. Do you see that? So that goes away. We're left with moles. That's what we're looking for. We got it. 1.58 divided by 35 point whatever is 0.045. And did anybody get something slightly different? If you did, it's because rounding differences, okay? Did anybody try it in their calculator? Because in my notes, I didn't round. So actually it's 0.0451 is what it is without rounding. What did you get with rounding? Exact same thing? Okay. So that's because these are really close, right? Rounding is okay when it's basically that number. Just don't round too much, okay? All right. Maybe we should practice calculating molar masses before we get into conversions like we did, right? So on section 2 of your worksheet, it says calculate the molar mass of each for each of the following substances. Little typo there. Should we do one that looks a little icky? Maybe the bottom one on the left side? Let's do that one together. So we got NH4 in parentheses, then 2 outside the parentheses, SO4, ammonium sulfate, right? Okay. You guys know how to balance equations pretty good yet? We count them just like balancing equations. How many nitrogens are there? 2 of them because of that 2 right there, right? So we have 14 multiply 2 plus, how many hydrogens do we have right there? 8 because we got 4 inside, right? Multiply the 2 here. So that's 1 multiply 8 plus sulfur is 32. There's only 1 because there's no parentheses. And then oxygen is 16, and then we got to multiply that by 4. And when we do this, we get something 28 plus 8 plus 32 plus 64 is 40, 104, 132 grams per mole. Just use a calculator, it's easier, right? The reason I'm not, because I don't have one here, okay? Besides my phone, and I don't like that as a calculator. Okay. So that's it. Make sense to everybody?
You should make that on the side.
Well, I'll tell you what, it will be on there. Probably more than once, but it might just be one of the steps in a problem, right?
No.
Because this is just a conversion factor, right? Yeah.
In the hydrogen, you got 1 times 8.
We got 4 hydrogens inside here, right?
Got you, okay.
But then it's multiplied by 2.
Got you, okay.
So if you want to write it out, we have NH4, and then we have 2 of them. So we have 4 here and 4 here, that's 8. Good? Easy way is just to multiply.
Yeah, I just don't understand the context of it.
Yeah, good. Do you want to try any others together, or do you want to just practice some for 1 or 2 minutes? Yeah? Yeah. Practice for a couple minutes? Yeah, do it.
Professor?
Yep.
So this means.
1 plus 12, not times 3.
3 hydrogens.
Yes, that's only 3 hydrogens, because there's no parenthesis around that, right?
Okay.
So it's just 3 hydrogens there. So it's 112, and then I guess we could have 2 12s because there's one right there, right?
Mm-hmm. But get rid of.
The 3.
Because it's not in parentheses.
Yeah.
Okay.
So now we have 3 hydrogens, so it's plus 1 times 3.
Which is.
Yeah. Does that make sense? Then plus a 12 there, 16 times 2. Yeah.
Okay.
Good?
Okay. So as long as it's not in parentheses, then I don't have to worry about multiplying. Right?
Yeah.
Okay.
The number, if there's no parentheses, the number just goes to the letter, the letter that it's next to, or the element that it's next to.
Right. Copy.
Good? And I don't know if these are rounded. How are you feeling? Good? Any questions? So here's the answers up here to check. All right, let's use this as a conversion factor. Ready to move on? All right, so let's determine the mass. If we have 2.45 moles of carbon dioxide. Okay? So before we can do anything, we got to what? Find the molar mass, right? So carbon has a molar mass or atomic mass of 12 plus 16 multiplied 2, that's 3244. Good? So we start with what we know, 2.45 moles of carbon dioxide. And we know for every 1 mole of carbon dioxide has a mass of 44 grams. And we get like 107.8 grams of carbon dioxide. Yeah? Questions? Yeah, Mina.
Sorry, where did you get 2.45 from? Or was that from the other?
That's given to us. If we start with 2.45 moles of carbon dioxide, we want to convert that to mass. Why? Because moles don't do us any good. So if we have moles, we got to get it to mass so that we can actually measure this out, yeah? We don't have a way of measuring moles. So we're just converting 2.45 moles of carbon dioxide to grams of carbon dioxide. And again, this is just a single step of where we're getting. Okay? Any other questions? Are we getting this? Okay, if we go to our worksheet, section 3 and 4. So section 3, we're converting grams to moles, and section 4, we're converting moles to grams. So let's do a couple of them that look a little icky. For example, we have 2.99 milligrams. So this is the bottom left example of lead 2 chloride. And we got to convert this to moles of lead 2 chloride. What looks different in this one? We got milligrams. But do we know how to convert milligrams to something else? And what are we going to convert to? Grams. We know how to do this. We should, right? So let's do it. So 2.99 milligrams of lead 2 chloride. So milligrams we don't want, they go on bottom. To grams on top. Questions on how we know what to do? We know we got to go to grams because we know a conversion factor of grams to moles, right? Okay. What's the conversion factor of milligrams to grams? 1,000 what? Milligrams. Does anybody like that method, or do you want to use the 10 to the some power? What way do you like in your brain?
Whatever's gonna be on exam.
Well, you do it how you want to do it. Yeah? There's two ways to do this. I like to use the 1,000 because it doesn't have an exponent. It's like, yeah, that's a little bit nicer, but you have to know what that means, right? So just remember, whenever you do a conversion problem, this top has to be the same value as that bottom. Double check that. So if we have 1 gram, let's use a different color here. If we have 1 gram, how many millis? What's a milli mean? 1,000th, right? Or 10 to the negative 3. And 10 to the negative 3, if you remember that, is 1 over 10 to the 3, right? And 10 to the 3 is 1 with 3 zeros. So 1/1000th, how many 1,000ths do we make to get 1? 1,000 1,000ths is equal to 1. They both have grams, so we know they're the same. Are we good with that? Does anybody just cringe at that, at thinking of that? Okay, so then do this way. Okay, so on our reference sheet that I gave you, or the prefixes that I had you write down, do you have that in your brain? Okay, then we do this. 1 milli anything, whether it's a gram or meters or liters or whatever, is the same as 10 to the negative 3, right? Do you like that? Anybody? Well, if you don't like that, I would stick with the other one. Because, watch, 10 to the negative 3 means milli, right? What's on top is on bottom. It's the same. They both have grams. They're the same. Or, if you know 10 to the negative 3 is equal to 1 over 10 to the positive 3, that's the same as 0.001, right? Or you can divide 1 divided by 1,000 is 0.001, and you can put that right there. A lot of different ways to do it, guys. What's the best way? The way that works in your brain. If none of them work, you got to figure out which one you want to try and just get good at it. Yeah? Which way do you want me to do it? The 1,000 on the bottom? Okay, so we got 1,000 milligrams is the same as 1 gram. That goes away. Now we have grams, now we need to go to moles. Grams of lead 2 chloride to moles of lead 2 chloride. Oops. 1 mole has a mass of what? We got to figure this out. Is this 207? Going from memory. Don't go from memory. You don't have to memorize these, right? 207 plus chlorine is 35.5, so that's what? 71? 35.5 times 2? So that's 278. Good? That goes away. Are we going through these too quickly? And we're left with, that's all we're left with is moles of lead 2 chloride. That's what we're looking for. That tells us we can stop converting. And we just multiply and divide. And we get 1.08 times 10 to the negative 5 moles. Of lead 2 chloride. We okay? Should we try one in section 4 real quick? Try this micro one. We have 21.2 micromoles of CH3OH. It's like, what, micromole? Do we do it the same way, guys? Yeah, micro, the prefix is the unit prefix. A mole is just a different unit that we learned today. It's the same thing. How many micromoles are there in a mole? A micro means 10 to the what? Negative 6, or 1 millionth. So we need a million millionths to make 1 mole. Good? Well, is that the way you want to do it? Okay. So we want to convert this to grams. So we start with 21.2 micromoles of methanol and 1 million micromoles is the same as 1 mole. Are we good with that? We're not there yet, so we keep going. Find the molar mass, and we convert moles to mass. Finish that. Do you want to finish that one? Okay. So, what's the molar mass of CH3OH? What is it? 32.01, or we could even just say it's 32, right? 32 grams of CH3OH. Did everybody else get 32? Okay. And that's what we're looking for, so we can stop. And that would give us 6.79 times 10 to the negative 4 grams of CH3OH. Good? How are we feeling? Is it okay or is it kind of rough? So we threw those in because you still need to know your prefixes. We're still going to use them. So don't forget about those. All right, do you need any answers for your other ones? Should I put the answers on the screen? Or how are we feeling? Do you want to keep practicing? Do you want to move on? Practice? Or move on? What about everybody else? Moving on? Okay. So we have about 35 minutes or so left. We can stop if you guys feel like, oh, we're burned out, or we can keep going. So I allotted time to have 2 days on each chapter, 5, 6, and 7. But then we won't have any time to review. So you tell me what you want. I don't want to burn you out. I feel like I burned you out last time, right?
What's the exam the first day we come back
From break?
Yeah.
Let's see. No. So we have, next week we have 1 day, yeah? So we can finish up this chapter next time. And then we'll have fall break. And then we have another week for chapter 7. And then the following week is the exam.
Sounds good.
How are you feeling? Do you want to? It's up to you. Who wants to keep going? One or two of you? Who wants to just, we've had enough? 3 against 2. Uh-oh. That's not good numbers here. The rest of us don't care?
What are we gonna be, we're gonna be doing this again, or what are we?
Yeah, we're going to be doing more of this. So we just learned 2 steps, guys. We're going to learn one more step and put it all together. Learn at least one more step. Maybe not put it all together tonight, but one more step. Okay. So really, we're going to just put these 2 together. No, let's just learn one simple step real quick. Okay. So if we have water, this is a ratio of 2 to 1, right? 2 to 1 what? 2 atoms of hydrogen to 1 atom of oxygen. Do we know that? Do we get that? Okay? But I want to show you something with what we just barely learned. if we have two atoms of hydrogen, and ladies and gents, I told you we're probably never going to use 6.022 times 10 to the 23 in real life, right? But here is why we learned this. Okay? We learn it for this reason. So you can either just watch or you can write it down. I'm not going to test you on this. I'm just showing you why we know 6.022 times 10 to the 23. Okay? So 2 atoms of hydrogen. Now let's convert this to moles. Okay? And I'm just going to do this. If you want to write it down, you can. I'm not saying don't, but I'm saying you don't have to. So 6.022 times 10 to the 23 atoms of hydrogen. Good? What goes on top? 1 mole of hydrogen. You follow? So let's type this in our calculator. 2 divided 6.022 times 10 to the 23. And we get something like 3.32 rounded times 10 to the negative 24, right? Yeah? And that's moles, so atoms go away, moles of hydrogen. Okay? Now let's do the same thing with oxygen. We have 1 atom of oxygen. And we do the same thing. 6.022 times 10 to the 23 atoms of oxygen to 1 mole of oxygen, right? That goes away. And then, okay, we got to do this again. Let's just 1 divided by 6.022 e to the 23. 1.66 times 10 to the negative 24 moles of oxygen. Are you following me what I did? Okay. Now, our ratio of atoms to moles is 2 to 1. What's our ratio of moles to moles? If we divide these, we get 2 to 1. So, if you guys want to keep using 6.022 times 10 to the 23, we can. Or we can just use moles. Isn't that nice? Yeah, Mina.
Sorry, I lost you at one step. So how did you get 1.66? Did you?
I did 1 divided by 6.022 times 10 to the 23. I just converted 1 atom. Do you know why I did 1 atom? Because the ratio is 2 atoms of hydrogen to 1 atom of oxygen. So I converted this into moles and this into moles. Just to find the mole to mole ratio. Yeah?
Oh, and then the top one you did 2 divided by 6 point.
Yeah. Uh-huh.
Okay, sorry, that's where I got lost for a second.
Are we good?
Yeah, now I got it.
Yeah, thanks for asking. Now, if we take this and divide it by this, what goes away, guys? These go away, right? If we divide those two, and then we still just get 2 over 1. It is 2 over 1. If you don't believe me, you can plug it in and try it. So since that number is the same for all substances, then we can just treat this water as a 2 to 1 mole to mole ratio. Good? And then we don't have to use 6.022 times 10 to 23. Isn't that nice? Okay. So, yeah, question.
So, okay, sorry, I have a question. So basically what you're saying is that let's just as an example to keep it simple, let's say it was H3O, this is an example.
Uh-huh.
Then it would be, we would automatically know it's a 3 to 1 ratio because it's
3 to 1 mole to mole ratio, yes.
because it's gonna be like the 3 hydrogens divided by
That's right.
6.022.
Because it's still divided by the same number on both of them, and they're gonna just cancel out, right?
Okay.
Yeah, same. So if we have carbon let's do C3H8. How many moles of carbon to how many moles of hydrogen do we have? 3 to 8. Yeah, okay. And so, well, we learned how to balance equations. We got this down? Okay, so for example, we have iron 3 chloride breaks down into iron and chlorine gas. Now, we have to balance this before we do anything. Otherwise, it's just an ingredient list, right? And we need a recipe so that we know how we make good food, right? Or whatever, okay? So we got to balance this. Let's start with chlorines because that's the biggest number. We have 3 on one side, 2 on the other, so what do we do? Least common multiple, right? Well, what's the least common multiple of 2 and 3? 6. So we're going to put a 2 right there and a 3 right there. Good. Irons, there's 2 on this side, so we better put a 2 right there. You follow? And if you guys need to split it up and show your work, do it. Really do it. And if you want me to, I will. Just let me know. Okay? But right now, I just did this so that we can know something here. This is 2 what? 2 molecules? 2 molecules of this to every 2 molecules of that to every 3 molecules of that. Is that right? But if we use molecules, we're going to have to do what? Use 6.022 times 10 to the 23. But we know it's basically just moles, right? Well, it is moles. So the ratio, we have 2 moles of FeCl3 for every 2 moles of Fe because of the 2 there and a 2 there. You follow? And another ratio is 2 moles of FeCl3 to 3 moles of Cl2. And another ratio, can you figure this out? 2 moles of Fe for every 3 moles of Cl2. And there's 3 more ratios. What are they? The flip-flop versions. You get that? And so this is our last conversion that we're learning. And we use this to convert from one substance to a different substance. Now you might ask, why would we want to even do that? Well, it takes iron 3 chloride to get iron and chlorine. Can we predict how much iron we make? Or maybe better yet, what if we need 5 grams of iron to actually use somewhere, right? So should we just keep doing this until we get 5? Or we can just calculate it to predict how much we actually have to make 5 grams of iron. I don't want to show you right now, but that's the conversion factor. So let's do a simplified conversion factor. Let's say we have, let's say we need 3 moles of iron rather than grams to keep it simple, okay? And we want to know how many moles of iron 3 chloride do we need in order to get 3 moles of iron? Good? We might also want to know how many moles of chlorine gas will we get? We can do any of those. It's just a conversion factor. So we take what we start with, 3 moles of iron. And we don't want moles of iron, so that goes on bottom, just like normal. Nothing's changed. And if we want to know how many moles of iron 3 chloride, then that goes on top. Good? And what's the mole to mole ratio? 2 to 2. What happens if we don't balance our equation correctly? Then we're going to be off. So that's important. You have to make sure you have a balanced equation. So double check it before you do this. Otherwise, you're wasting your time. So it's a 2 to 2 ratio. So how many moles of iron 3 chloride do we need? Just 3, right? Because those go away. We need to start with that much if we want 2 moles. How many times are we 100% perfect in lab? Almost never? Yeah, so we might have to get a little bit more just to make sure we have enough, right? But we know we don't have to get a ton more, okay? Because it's pretty close. We can also start with, if we know we need 3 moles of iron, we can figure out how many moles of chlorine gas that we're going to also create. Even though we're starting with moles of iron, we can do this. So we don't want moles of iron, so that goes on the bottom, just like before. And we want to find out how many moles of chlorine gas we get. So what's the mole to mole ratio? 2 to 3. We just use those coefficients in our balanced equation. So 2 for chlorine, 2 for fluorine, for iron, and 3 for chlorine. That goes away. And then we got 4.5 moles of chlorine gas, because 3 times 3 is 9, divided by 2. Good? Pretty cool, right? Now, moles isn't very useful, is it? But we already know how to convert moles to grams and grams to moles. So we just tack another one of those conversion factors on each side, and we can go from grams of one substance to grams of another substance. Do you get that? And that's what we're going to do next time, is put it all together. It's just 3 steps, guys. Actually 4, because you got a balanced equation, right? 3 conversion factors. But we know how to do them, I hope. If we don't, practice that and come next time so that we're ready for it. Good?